Hello, everyone. Welcome to the ECS Deep Dive. My name is Brent Langston, and I'm a developer advocate with the Container Services team. And that's the team that brings you ECS, EKS, Fargate, ECR, AppMesh, and some other services. So I want to talk to you today specifically about ECS. So we're going to take a look at ECS. We're going to go over kind of some history, but then we're also going to talk about some specific advanced features of ECS. Now, this particular talk is labeled Con 402, meaning it's a 400 level talk. It's advanced. We're talking about advanced features, but I don't want you to think that it's complicated. One of the design principles that we have with ECS is we try and make things as simple as possible. So we're going to take some of these advanced features, some of these advanced topics, and I'm going to show you, hopefully show you, how simple they actually become when you're doing it on ECS. There are some other related breakouts that you should be aware of. We just had Con 201, which was an overview of using containers on ECS. And then we're going to have next up Con 303, mastering EKS, and then Con 404, getting your code all the way to a running container. So let's talk a little bit about some history so that we understand why we are where we are today. Some background for you about me. I actually helped build Tumblr and Spotify, and then went on to be one of the founding engineers and architects at Oscar Health, and then re-architected and was the platform director for Cloud Passage. So I've been running microservices in production at scale since really before Docker was around or was popular. So I definitely understand some of the pain points of operating at that kind of scale with thousands of services. So to understand why things work the way they do today, it's handy to sort of have a bit of history and a bit of context. And so we look back to running services on instances. And the common pattern back then was one service, one instance. And if you needed to scale that service up, you add instances. And of course, adding instances was slow. It took, if you had great automation, it took several minutes. Configs had to be edited. These new instances had to be sort of accounted for by the rest of the platform, and so on and so forth. So it was painful, but manageable. The tooling that existed around doing that was also tended to be language specific. When it came to, for example, deploying a service, you would write tooling that would deploy a specific language. So you would find organizations that would try and standardize on one or maybe a handful of languages because they were investing in writing the tooling and writing the automation for those languages. Well, Docker came along, and Docker solved some of these problems for us. One of the problems that it solved is it standardized the way we distribute, the way we package our code, and what goes into that packaging. We can package the code plus all of its dependencies into one deployable artifact. And the deploy mechanism is now standardized as well. So we don't have to limit our service teams anymore about what languages they're allowed to use. They can be free to use any language or whatever makes the most sense for that service team. So Docker really helped with that. Another thing that it helped with, though, was it actually allowed us to put more than one service onto an instance. So we could now run services alongside each other a lot easier than we could before. So we were able to get more density for our services. So containers have now become the standard way to ship and run our application in the cloud. But Let's look at, for example, the mechanism that we had once people started using containers. There was a person, an operator, who would deploy a container or set of containers out onto an instance. And that often, at the most basic level meant they were SSHing into an instance, Docker pull, Docker run, etc. Or they might use some kind of automation to do that for them. But they were tying the container to the instance still. Or they were tying maybe a set of containers to an instance. So if they needed to scale a service or a collection of containers, they would have to still add instances, right? So once we started going all in with containers and putting all of our logic and our resources and our application into containers, what was left on the operating system? Very little, basically nothing. So the operating system itself became dumb. Not dumb, but less important. So we didn't have to care as much, right? That could just become a pool of resources. So this is going to be a reoccurring theme, by the way. At AWS, we're always looking at what are our customers doing, and we're trying to understand how can we make things better for them. We do that by listening to feedback from them, by hearing what they're telling us that they have problem-wise, but then we're also just observing what they're doing and trying to see, is that something that is happening, commonly over a lot of our customers, and can we fix it? Can we make it better? So what we did is we built ECS. And ECS is this container orchestrator. And what we decided to do was take a different approach to managing software and managing processes. Instead of trying to figure out, how do I run 3 containers on instance A and 5 containers on instance B, all I should have to do is have you describe what you want. Describe the end state. So launch 10 copies of my container distributed across 3 availability zones and connect them to this load balancer. Just send me that description and I'll go out and make it happen on your fleet of servers. So that's what ECS does. You describe the end state that you're looking for, and the orchestrator figures out how to make it happen on just a pool of resources. So nodes no longer are individual, they're no longer important, they are just a fleet of resources. So, ECS has been around for several years. Let's take a look at what we've done with it in 2018. The velocity of enhancement is actually pretty impressive. We've increased launch times, we've added a GPU pinning feature, we've added app mesh preview, we've updated the CLI support for Docker, we've added SSM parameter support, ECS agent signing, service discovery, and target tracking and autoscaling. So we've done a lot, and this isn't even a comprehensive list. This is just sort of what I could remember thinking back over the year. What I want to do is talk to you about these 4, because I think these 4 are really handy and really good problem solvers for existing problems that people are fighting with. So Daemon Scheduling. Again, make this easier for us. Prior to us launching this feature, Daemon Scheduling was something that people were trying to figure out how to do. They were working with what they had, but they were working, they were coming up with workarounds for this feature. They were looking at, what's the size of my autoscale group? And then they were deploying a task or a service that was sized so that there would be one deployed to every host, for every host in their autoscale group. So Daemon Scheduling was something that we said, oh, look, this is an easy solution for us. We can come out with this feature and solve a lot of problems. So this specifically deploys a task to each cluster instance. So instead of having to figure out how many instances do I have at any one given time, which with autoscaling is not trivially easy. You might only have one autoscaling group if you have a very simple platform. But a lot of people actually have 3 or 4 or 5 or 10 autoscaling groups, and they would have to do math and figure out how to add all those together to come up with the right number to deploy. We can take care of doing that for you. And oh, by the way, if you add another node group, we'll roll that into the calculation as well. So for you to do daemon scheduling, now all you have to do is scheduling strategy daemon. It's very simple. So we took something that was complex that customers were struggling with, and we made it very simple. And then once you've launched that task, this is the feedback that you get back, scheduling strategy daemon. By the way, I've highlighted the important parts. Scheduling strategy daemon, like we saw before, but then deployment configuration, you see maximum percent and minimum healthy percent. This is how we control the way this service rolls out. You're probably familiar with the term blue-green deploy. Blue-green means roll out all new containers before we kill off the old one. But for the case where you only want one running for any given instance, you wouldn't want to do a blue-green deploy, because then there'd be a period of time where you have 2 of those containers running at the same time on the same instance. So this is how we do a red-black deploy, where we kill the container and then we bring up its replacement. So minimum healthy percent 0 means we're allowed to go below 100%, and then maximum percent means we're not allowed to go over 100%. You can see more. I highlighted the important parts of the documentation, docs, Amazon ECS, developer guide, ECS services. That's a good thing to have, ready to click on it for lots of different features. The next one, target tracking autoscaling. So this is another thing that we were hearing. Autoscaling is a feature that we added to containers. So just like before, you could scale instances. You can also scale containers directly using autoscale groups. But figuring out the right thresholds, the minimum threshold and the maximum threshold, can sometimes be complicated. Well, really, if you stop and think about it, there's one approach that to me, it makes the most sense. So this is the approach I tend to take with my microservices. Instead of trying to figure out upper and lower thresholds, what I do is I benchmark the service, and I find out this service can handle X number of ops per second. And then I turn around and I back off from that number a little bit, and I set that as a target tracking service. So for my example, I actually have a Ruby application, and it can handle 1,400 ops per second. That was the benchmark. So I'm going to set this to target track 1,000 operations per second. And then as I get requests that come in, I'll actually scale up so that each target is trying to maintain around 1,000 operations per second. And then as requests die off, I'll scale back down so that, again, I'm still maintaining 1,000 operations per second per target. The way you set it up, very, very simple. You can use the AWS CLI, register scalable target, and notice the scalable dimension is desired count. So I'm setting the scalable dimension to the number of tasks that are going to be running, and the resource ID in this case is my task, the ECS demo front end. And I'm also setting minimums and maximums. So minimum 3, maximum 25, because I don't want to necessarily, scale to infinity, because I might not be able to pay for that. And I don't want to scale down to 0 all the time. I want to always maintain some kind of presence. And then you create a scaling policy. And the scaling policy, you can see I have a JSON file that's configuring it, and I'm giving it a name, track ops per target, and the target value I mentioned was 1,000. So I'm setting the scaling policy to track 1,000 operations per second. Now, where does that metric come from? Well, this particular service is tied to an ALB. And ALB includes some metrics built into it. One of them is requests per target. So I'm actually just reading those metrics directly from CloudWatch from the ALB metrics. So when I do that, and by the way, this is a screenshot from when I ran Apache Bench against my service. The dotted red line is 1,000 operations per second, and so you can see that I started sending it some traffic, and this is kind of an abnormal pattern. A more realistic pattern would have been a much gentler curve, but in this particular case, it was a spike because I started hitting it with all of my traffic all at once. But you see that we spike up, and as soon as we cross that red line, the default is for 3 measurement periods, which are 1 minute. So for 3 minutes across that red line, we start to scale out. And we also scale based on the amount over that line we've gone. So if we're double our line, if we're running at 3,000 ops per second, we're going to add 2 additional targets. So we're going to go from whatever we're at now, we're going to double it or triple it or whatever that math works out to be. Once we've been running for a while, notice how the graph tapers back down. That's not because we're getting less traffic. Remember, this is traffic per target. So because it's per target, the total count can still be going up, but the per target count is going down until it's finally below that red line again. And that's when we're considered healthy again and we've scaled fully to our correct capacity. So when I got up on stage, I actually launched this on my laptop. So let's see what's happened. So I launched this when I got up here, and notice you can see the scaling has kind of had an effect where I've been able to take some traffic. We added a target, I'm sure, is why this dipped down substantially. And then because of that, Apache Bench was able to probably send it even more transactions than it was before. So we went up a little bit and then tapered back down a little bit. So we'll kind of seesaw until we get that back down below this line. But in only a few minutes, I'm scaling out. And if I look, I started out at 2 running tasks minimum instead of 3 like on the slide. And I'm now up to 6 desired and 5 running. Sorry, I realize this is probably too small for you to see. So 6 desired and 5 running. And if we look at the actual tasks, now all 6 are running. So it's very simple at this point to figure out how to scale out, how to scale in. I'm going to go ahead and kill this traffic. I don't know if we'll see the scale in part because there's a pretty conservative cooldown. We don't start actually scaling back in. This is all customizable, but the default is to wait 15 minutes before we start scaling back in. But think about what this does for you from a budgeting standpoint and from an operational standpoint. I just had to set 2 parameters, and all of a sudden I was scaling my service, and I don't have to create or manage any kind of time series database or metric service or anything like that. I don't have to figure out how to scale a metric service, or I don't have to send requests to constantly be polling or reading from that metric service. It's just all built in for me. So this is a sample from the events that occur. So if you wanted to watch for a log of events or something like that, in the ECS event log, you can see that as we scale out, you'll see, for example, successfully set desired count to 7, and then we started another task. We registered it with the target, the ALB target, and then it reaches steady state, which means we start sending it traffic. It's not specific to Fargate. It's an ECS function. The question, by the way, from the audience was, is that specific to Fargate? I'm running these on Fargate, but this could just as easily happen with EC2-based ECS tasks. So it's not specific to Fargate. If you want to check out the demo, I've actually put it on GitHub so you can run it yourself, and you can see how easy it is to set up autoscaling for your service. Service discovery is another thing that customers were struggling with. And they were trying to figure out, what's the best way to do service discovery. When I was at Spotify, this was again before containers, we actually did service discovery using DNS. And this was before Console or any of the other DNS-based service discoveries. So it was cool, it kept things simple, but it wasn't oriented for containers. So again, it was oriented for instances. An instance gets one IP, and at that one IP, we expect to be able to reach this one service on this one port. So what if we could have that kind of simplicity again, but with a container? Well, with ECS, we have the option of attaching an ENI directly to the task so that all the containers in that task are at an individual IP address and have their own port range that you can run services on. So we can have that kind of simplicity. So then the next step is register it with a service. So we use CloudMap for that. And CloudMap actually ECS, the control plane, talks to CloudMap, and as tasks come up and go down, we register and deregister them with Route 53 using CloudMap. So we also, by the way, have an HTTP UI or HTTP interface for that as well, but I find the DNS interface to be more than adequate. So this is kind of what that architecture looks like. But again, you don't have to build this, and you don't have to run this. You simply check a box, and you get it for free. So as traffic comes into your load balancer, it needs to be routed to your containers. So your front end is probably tied directly to your load balancer. But how does your front end find its back end services? That's a great use case for service discovery. So instead of trying to keep track of where all those back end services are running, or instead of running another load balancer for them internally, we can actually just give them a DNS name. And then we can just start talking to that DNS name. So this is how we do that. So I'm bringing up a back-end service, ECS demo Node.js, and all I'm doing when I'm bringing it up is I'm saying, create a private DNS namespace. So it's private only to the VPC. It's not accessible from outside the VPC, and I'm just giving it a top-level domain of service. So I'll end up with a name, ECS demo Node.js.service. And then enable service discovery. That's the command line way of checking that box that I want to have the service discovery feature. So then my front end, when I'm defining, this is a Docker Compose defining how to talk to the back end. I'm just passing an environment variable. The environment variable key value pair Node.js URL equals, and I'm telling it to direct traffic to the DNS name ECS demo Node.js.service. So there's a demo for this as well. This is actually, by the way, ECSworkshop.com is a workshop that I debuted a little over a year ago here in Tel Aviv. So I'm happy to be back to talking about it again. Definitely check it out if you haven't already. But let me show you this demo where we have the front end and back end services running. Well, let's see here. Okay. So don't worry about the text on the right. I know you probably can't read it, but it's really for me to make sure that I don't forget what to show you. But I have a front end talking, and then I have the ECS demo Node.js, a back end API running, again, in Fargate in a VPC. And if I just do a simple dig for ECS demo Node.js service, I get back 3 IP addresses. I have 3 instances of those running, 3 tasks running. So just like this particular workspace, any service that's in that VPC can do a simple DNS query and know how to go talk to that API. Let's actually watch that. Let me figure out how to zoom out my screen again. There we go. Okay, so now we can see in the upper left corner, we can see all of the IP addresses that my task currently has. And again, the front end is free to connect to any or all of those. If you're familiar with the workshop, then you've probably seen this before, but what we end up deploying in the workshop is this. So this is, I wanted a set of applications that's so simple that you won't ever get hung up on what they're actually doing, and instead we can focus on how they connect to each other and how you set them up. So what we're working with, what I'm about to show you and work with, is the green line, the Node.js line. And you can see that currently we're hitting, we have 3 copies running, and they're distributed across availability zones. So one in 1A, availability zone B, and availability zone C. Let's kill one and see what happens to our service, to our front-end service. First, let's get a set of running. Let's see the running tasks. So there's our tasks that are running. And I'm going to pick, let's kill the one that's in zone A. Oops. Recopy this. So I sent the kill command. Now that's going to take a few seconds to propagate from the orchestrator down to Fargate where it's actually running. But what we should, well, there it happened. So now we're down to, and again, we have multiple authoritative servers, so that also needs to propagate to all of our servers. But you see we're down to 2. Let's go back here, and our green one, we're really only hitting B and C right now, right? Now, the service itself, that API endpoint, that IP is still alive for a few more seconds because we take it out of service before we actually kill the task. But once it's been out of service for a few seconds and we've killed the task, let's come back over here, we'll see the replacement task pop in a few seconds. And there it is. The 100.15 is the replacement task, and we're already hitting AZA is starting to take traffic again. So what did I have to set up to have service discovery for my cluster, for my services? Nothing. I had to check a box. So we try to keep things simple. We take complicated topics. Instead of having you run a control plane for this, instead of having you figure out how to upgrade a service every time there's a new version that comes out, we take care of it for you and we run it for you. Okay, the last thing I want to talk about is GPU pinning. And this is probably the most recent big feature that we rolled out. So what is GPU pinning? Well, before we had this feature, customers that wanted to run machine learning training on a cluster, they would have to figure out weird workarounds to launch GPU-based tasks onto their cluster and have them hit the appropriate type of instance. So the type of instance that's good for that kind of training are P-series instances. So you could potentially set a constraint, only run this on a P-series instance. But you wouldn't necessarily have a good understanding of how many GPUs are available on that instance. And if I launch a task on that instance and it takes up all the GPUs, then that instance is no longer available to schedule future GPU-based tasks. So we built GPUs directly into the scheduler. So now they're a first-class citizen, and you can request them. And you can say, I need 4 of them, or I need 8 of them, or I need 1 of them. And we'll find that out on the cluster and schedule your task, or we'll tell you, sorry, there aren't any available, and we won't schedule your task. And the way you do that in the task definition, you just simply say you have a resource requirement of GPU and the count. So you can say GPU 1 for me running this TensorFlow container. And then when you're, well, heck, let's just do it. So I've done that in a task definition and registered that task definition. So if I run, in fact, this is, by the way, the one demo that's not on Fargate, and it's because I needed a cluster that has GPUs. So I wanted a cluster that I could launch some training on and have those tasks run using a GPU. So I have a cluster that has 2, I don't remember, regular instances, and then 2 P316X larges. So that's where I hope that these tasks are going to get, it's where I know these tasks are going to get scheduled on. So each of those 2 instances has 8 GPUs. So I have a task definition here that's requesting 8 GPUs, and it's going to launch a TensorFlow container that's going to make use of those 8 GPUs. So you can see in the output, it tells me the GPUs that are assigned, and now if I run that task again, I'm scheduled another 8 GPUs. If I try and do it a third time, I get back errors saying, hey, wait, the resource GPU can't be met. So this is a good way for me to fail fast and understand that I can't run this task because I'm out of resources. So I could either then choose to scale up or wait and run that task once the first 2 are done. If we take a look at my cluster, we see my 2 TensorFlow container tasks, and they're pending right now, so we'll wait for them to, that's a big container. It's like a gig container to download and run. But they're running, so we'll go and look and see if we have any log data yet. So these are running a TensorFlow benchmark, actually, and it takes, I think it ends up running over the course of about 60 seconds, but it takes a while to warm up and get the data ready to run. So here it is coming up, and you can see that we, in the task definition, requested 8 GPUs, and somewhere in here in the logs, we'll actually have a record of the GPUs that were assigned. I think this line right here, yeah, you can't see it, but 0 through 7 are the GPUs that were, there we go, 0 through 7, the GPUs that were assigned. So these are not only assigned to this task, but now they're not available for scheduling other tasks. So we've pinned them to this task, and they won't be usable until this task is completed. So again, the output is directly in the output from when we launched the task. And you can see this, you can run this demo yourself from this link if you want. So let's review real quick. ECS is an orchestrator that tries to make orchestrating microservices easy. And we're constantly adding new features, but we want to keep your operational responsibilities simple. So we want to add features without adding more work for you. And then, for examples, Daemon Scheduling, launch a container out onto every instance. It doesn't matter how many you have. Target tracking Autoscaling, just keep the Autoscaling set to the operations per second that you're looking for. You can also track based on CPU utilization or memory utilization, if that makes more sense. And then service discovery, check a box, get your IPs registered with Route 53, and then have that be available inside the VPC to everything else that it might make use of. And then GPU pinning. Allocate GPUs just like you do memory and CPU so that you know when you've run out of them, and you can make a decision about what to do about that. These were my See More links, my demo links, if you want to take a picture of that or have that available. I think you'll also get a copy of the slides after this. And that's it. So I'm going to be at the back if you have any questions, but I really appreciate you guys coming out and listening to the talk about ECS.